Hello and welcome to the fourth episode of my Arduino tutorial series. Today we're going to be making a synthesizer that lights up an LED in a different color with each frequency. How we're going to be doing that is we're going to be taking a look at the notes library we're using. We're going to be making a frequency function using that data. We're going to talk about the linking of color to sound in a somewhat arbitrary method. We're going to learn about scale construction and how we can use our frequency function to construct a pentatonic scale from one frequency. And then we're going to be making an actual noise and mapping that scale to 5 buttons. And finally, we'll be adding a joystick and a knob to change the gating and the arpeggio, as well as pitch of the synthesizer. So here's the general idea. It's a system with 5 buttons that each cause a speaker to play a different note in a scale. We have a knob to modulate the gate of the note and a joystick to modulate the pitch. Holding multiple notes creates an arpeggio, and holding one note makes that note play over and over again. Now let's talk about some of the concepts we've used. First, let's talk about the notes library. The notes library is just a header file that defines all of the chromatic notes from C0 up 89 notes and their frequency values. The problem with this right now is that we can only ask for each individual note, and typing an array that would contain the scale we want would work, but would complicate the fact that we want to modulate the note up in pitch without knowing its name some of the time. Also, we want to be able to play tones in between notes, and right now we have to write in more variables to our header function, and we'll never get all the notes in between them anyways. We're going to use the data we have here to determine a mathematical exponential function, because that's how frequency behaves in the spectrum from low to high, and that will represent all of our notes plus the ones in between. Let's look at how we're going to create this frequency function. To come up with this function, I used a graphing calculator to plot the notes' positions and the frequency to come up with our a and b variables for the function in the form of a times b to the x. The position of a note is where it is in the ordered list of 89 notes in the header file. To get this information to begin with, I went in my header file and I deleted all the comment that it had at the top of it. Then I used the line numbers in Notepad++ to determine that there were 89 notes defined. So I used this 1 to 89 as well as their associated frequencies, and made a list of plotted points that I put into the calculator. It did its calculator magic and it popped out with these 2 numbers. Now we have a and b, so we can construct this function. In this function, y would be the frequency that we end up with, and x would be what position of note. So every time the x goes up by 1, that's like going up by a half step, but it doesn't matter where you are in the spectrum. Next, let's talk about our method of linking sound to color. Since there's no real way to do this, we're going to be using a method inspired by this video. This is the general process. We multiply the frequency of a note by 2 for 40 times to get it up into terahertz territory. Then we use a formula to convert terahertz into wavelength, and then use that wavelength in another function to map the wavelengths of visible light onto a red, green, blue value so that we will send to our multicolor LED. Now, even though this procedure is somewhat arbitrary, there will be a definite color for each note in range. Now we write 2 functions, getFrequency, which takes in a note position and spits out a frequency, and its inverse, getPosition, which takes in a frequency and spits out its position. These functions will be built from the information that we got from our graphing calculator. Now we have the power to know the position of a note given its frequency and vice versa. This will be useful to us for the rest of the program. The first thing that we'll do with the information that we can now get from get frequency and get position is to build the function called construct scale, which takes a root note frequency and finds the other notes in the scale using whole step, half step patterns by noting that our positions of our notes have a difference of 1/2 step, and then using that position information to find all of the frequencies at those positions and putting this information into 2 arrays called current notes and current note frequencies. Now let's actually make some noise and map a scale onto the buttons. Setting up our buttons and the debounce function is pretty much exactly the same as we did it in the last video, except for this time we have 5 buttons. So all we do is we just put the statements that we used in a for loop, and it will go through all of those buttons individually. We'll know what button is pressed by what iteration of the loop that we were in, which we can get from the variable that we used to initiate that loop. Now that we have a reaction to the button presses, we write a function called playNote that takes the position of a note and plays the associated frequency. This is information we get from what the array construct scale is populated with, as well as what buttons we pressed. We'll use the fact that construct scale and buttons are always in the same order and have the same amount of items, so that each button will be associated with a certain point of construct scale, so each button will play the same sound each time. As a general overview, playNote plays the note for the time note timer, which we'll later control, converts the pitch to an RGB value using a function called pitch to RGB, which we'll talk about in a second, which utilizes our hertz to terahertz to wavelength to RGB method, then turns the light on in that color, waits for the time the note is on, then turns the light off. Finally, we'll talk about modulating the sound and the arpeggio. Originally, I was just going to modulate the sound using pitch, but I noticed when I took away the part of the code that set my last button states to the current button states, I could just hold the note down for as long as I wanted. Then, when I divided the note timer in half on the time when it was playing the tone, while leaving the delay for the light being on still being note timer, I got a nice staccato sound. And furthermore, if I held 2 keys at once, it would run through their loop logic one by one, giving me a basic arpeggiator, so I kept it this way. I connected a 10K pentometer to an analog pin as well as a joystick to 2 other analog pins, then both of them to 5 volts and ground. I directly linked the pentometer's input value to note timer. It's a range between 0 and 1024, and this would be in milliseconds. For the joystick, I created a variable called xmod to hold the values of one direction of the joystick using analog read. Then I mapped these values from -75 to 75, because this number is just in range that sounded good from my speaker and also allowed all the notes to be in a wavelength that was actually within human vision. We calculate xmod every frame in loop. Now that we have xmod, we can go into playNote and add xmod to the frequency that tone plays, as well as the frequency that's being the input to our pitch to RGB function. Caveat is the pitch will only change once the note has been played and it goes on to the next note. So it isn't an actual pitch bend, but this is what I've figured out. The closest you can get to a smooth change of tone and color is to turn the pentometer up in resistance so the delay between notes is very fine. Alright, let's take a closer look now at all the variables and the functions. We have the speed of light, which is obviously the speed of light. This describes what pins the LEDs are connected to, or it's one LED, but it has 3 pins, so it goes to 3 different pins. Red, green, and blue. These are the buttons. I have 5 of them, and they're on pins 4, 5, 6, 7, and 8. The buzzer is on pin 3. Use analog pin 0 for our pentometer modulation. And for our joystick modulation, we use pin 2, and for X and Y, pins 1 and 2. This 2 is a digital 2, it's digital pin 2, and this Y is analog pin 2, although we never actually use this variable in this code, but we could later. This is going to be the modified number of the X of the joystick, so we can put it into the range that we want. These two numbers are the numbers that we got from our graphing calculator and our information from this header file. This is the scale pattern, and these numbers in this order represent a pentatonic minor scale. So the root note is 0 half steps above the root note. Obviously, the next note is a minor third, or 3 half steps, and then they just compound on to each other. This one holds the current notes that are in the scale, the current positions of the notes. This one holds the current frequencies that are in those positions. These two variables hold the current state of our buttons, whether or not they're being pressed or not. This one represents how long our note will play until it stops or it plays another note. These are actually the 3 values that we will eventually send to these pins. First we have setup. Setup is pretty simple. All we're doing is we're setting the pins to be proper modes. So our LED pins are going to be outputs, while our button pins are going to be inputs. And we're also going to construct the default scale. I've noted that this works the best for me, this note. Come to our loop function. In the loop function, we set note timer based on an analog read of that pin, of our pentometer. Here we are generating Xmod by analog reading on our X pin of our joystick, and then we're mapping it to -75 to 75 because that number just worked. I don't know why this says play sound, that doesn't make any sense. Ignore that. This part right here is basically, it's like the dead zone of the joystick, so it's making sure that if it's between these two, then it's, or if it's outside of these two, then it's outside of the dead zone. So yeah, continue doing that. And if it's not, if it's like less than 45 in both directions, then just make it 0, like you're not touching the joystick. Here we're debouncing all of the button states using a debounce function. It's exactly the same function that we used in the last tutorial, but all we're doing is now we have an array of current buttons and an array of last buttons. So we're just putting that part in a loop, and then we're putting this part in a loop, and this is the optional code that changes the behavior of the synthesizer if I have it in or out, but that's also in a loop. This is basically saying if the current button state is high and the last one is low, so if you're hitting it, then we're going to play note, and it's not the note B, I know that looks confusing, but we're playing note B as in this B. That's going to say play the note that's associated with that button, since we're looping through the buttons in right here, because we have 5 buttons. This is the debounce, exactly the same as our last one. This compares the state of the input with a 5 millisecond window to smooth the button response. Next we'll look at get frequency and get position. Get frequency, this is where we're using our variables that we determined in our graphing calculator, and we round this number because it will eventually be input as an integer. When you put a float into an integer, you lose the decimal place, making it always seem to round down. That's why we're adding 5, so if the number we're putting in is at least at 0.5, adding 0.5 will push it up into the next whole number. So even though it's rounding down, to us, it's rounding in the proper direction. Get position is the inverse of get frequency. Note how it's using logarithms because a logarithmic function is the inverse of an exponential function. And all that's doing is it's getting a note frequency and it's putting it in note position and returning note position. This one is just getting a note position and it's returning a frequency, a rounded frequency. Right, this is construct scale. This is how we actually construct a scale from one root note, and we're going to use our get position and get frequency functions to do that. So the first thing we're going to do is we're getting the index locations of the 6 notes in the chosen root note scale, and we're putting them in this array, current notes. We're going to get the position of that root note's frequency using this. And then we're going to add scale pattern one by one. So the first one will be 0 and it'll just put in the root note, the next one and next one, and so on. After we have that, we're going to use these newfound indices and we're going to get the frequencies that are actually represented by those indices. And to do that, we're just going to use our get frequency function and we're going to use our current notes that we just created as its input, and that'll give us all of the current note frequencies. Now we have a scale and we've basically made where notes are on the scale and frequencies bend to our will. So now we can finally play a note. First we use tone. That just sends a square wave at a certain frequency to a pin on the Arduino. We're going to send it to buzzer pin that our buzzer is on, and we're going to use the frequency that we're going to play is current note frequencies, the one we just made in the construct scale, and we're going to play the note, which is the input of play note. And if you remember back up here in the loop, when we call play note, it's associated with a certain button, 5 buttons, with 5 notes in a scale. It says 6 notes here because I ran out of buttons and I wanted to add the octave root note, but I only have 5 buttons, so that's why that says 6. So this so this says play a tone on the buzzer pin using the current note frequencies at the same position as the button you pressed, and also add any modulation that we've added with our joystick, and play this note for note timer amount of time, which is determined by our pentometer, and we divide that by 2 because it sounds better. It makes a staccato sound. Since the note will only play half the time, and then when it delays down here more than half the time, it takes another half of the note's time to start the note. So if you want more staccato sound, you divide this. And if you want more of a whole sounding note, I imagine you would multiply that, but I haven't tried it yet. Next, we're going to call our pitch to RGB function, which I'll talk about in a second, but that basically gets the color of the sound. And now we're going to use that information that we got from here, and we're going to write to the pins that the colored LED is on so that it will display that color. We're going to wait a delay of whatever the note timer is so that the light stays on long enough for humans to see it, and then we'll just turn the lights off. Finally, we have pitch to RGB. This first raises a pitch into the terahertz range by multiplying the note frequency by 2 40 times. And then once we do all that, we use this information and the speed of light to calculate the wavelength of this frequency. I had to add 10 to the power of 9 to move the decimal to a place to make this number easier to work with in the next part. Next, we have a collection of if statements to get different RGB ratios based on different wavelength readings. This whole part of the code right here was taken from an online source that does the same thing, and the numbers were fudged around to fit my needs. Basically what it does is it takes a wavelength and it associates it to RGB values. Finally, after we do all that, we assign these newfound values and multiply it by 255 because that's the maximum that you can output to the LED from the pins. This has been episode 4 of my Arduino tutorial series. Today what we did is we looked at our note library and how we utilized that to create a frequency function. And we used this function and some more math to link color to sound. Finally, we made a noise using the buttons and mapped certain frequencies onto certain buttons, and we modulated that sound in the style of a gate, arpeggio, and a slight pitch bend. Thanks for watching, and see you next time.